How does the sound pressure level vary during a handheld sweep? When you do a sweep in a room, it can be something like this. And then the operator is standing in the middle. I think I've done this graph now a couple of times. And you do a sweep like this, and you go up, and then you go around and back down to where you started. Something like that. Now, in this room, you will have large sound pressure level variations, which means that if we look at it from above, you will typically have strong regions near the corners of the room, and it's a bit more quieter in the middle. And this could be the same if you look at it from the side. You're gonna get similar results. And there will be various patterns of this. This is just for one of the room resonances, the eigenfrequencies. You will have many different combinations of these. And the thing is, the higher you go in frequency, the more of these maximum minimum positions you will get. So that it will become more and more like this. You're gonna have like strong region, weak region, strong, and they will come tighter and tighter the higher up in frequency you go. Tighter and tighter. Density maybe more dense. So we'll have many maximum minima, and regions like this. Anyway, you can see where this is going. If you keep increasing the frequency, these will eventually they will come so dense, so you won't really notice the pressure variations anymore. But how does this look like when you take a microphone? When you take your microphone and you sweep it through this area, what's it going to look like? I actually now have some real pictures here from my instrument. This is from a sound pressure level measurement I did a couple of days ago. And you can see here, the one on the left, this is 800 hertz. So it's pretty much higher up in the frequency band. It's up here in the range when I'm measuring impact sound pressure level. And you can see a whole sweep. I've been going through this pattern with a selfie stick and a microphone. So it's a pretty large sweep radius. It's pretty much constant. It's a flat line. And then you take a look on the right side here, you got 40 hertz. So this is in the very low frequency region. And here you can clearly see these patterns on how it's quiet, and then it gets stronger, and then it's quiet again, and it's stronger, and then it gets quiet, and that's the end of the whole sweep path. I go one complete revolution, noise, one pattern, from start to finish, and it looks more like a sine wave like this. This is at 40 hertz, but you will have similar results if you look at 50, 63, 80 hertz, that region. You will get very big variations. And pay attention to the scale here. You got the lowest points is somewhere around 55, and the top one is close to 80 decibels. So we're talking about, like, in this case, 25 dB difference between the most quiet point on the path and the loudest point on the path. And this clearly shows why it's important to get a spatial average of the room. You cannot just measure one position, because then you might get anywhere on this curve if you just measure one of them. So be very careful when you do low frequency measurements. If you're going higher up in frequency, then it starts to look like this, and you will get pretty much the same result no matter where you put your microphone in the room, but not in the low frequency region. And this is very, very important when you're working with timber constructions. Because in a timber construction, it's typically this, where is the mouse? There. When you have the impact sound pressure level here, L dB, LNT we could call it, and then we have frequency here, hertz. And as you could see here, this is the typical response of a wooden construction. A high energy content in the low frequencies, and then it goes down the higher up in frequency you go. So something like that, let's say. And when you do the evaluation to compare this with the regulations, you do a logarithmic addition of third octave bands. And that means in a logarithmic addition, these ones are the ones that will determine the whole finished sum. Because even if you keep adding third octave bands here logarithmically, they will have almost no impact whatsoever on the finished result, on the end result. So these are the ones that are critical in a timber construction, and this is also the region that looks like this when you measure it. So you got the largest measurement uncertainty is also the region that determines the whole end result in a timber building. And on top of that, annoyance is very well it's correlated. Annoyance correlates well with these low frequencies. So this is what annoys people, this is what determines the single number quantity, and this is also the region where you have the biggest measurement uncertainty. And this is why it's so fun to work with timber constructions, because we're somewhat, you could call it like uncharted territory. We're if you're measuring in concrete constructions, you don't really have this kinds of problems, because in a concrete construction, the curve would perhaps look more like this. You will have the critical frequencies that determine the measured sound insulation in a concrete construction is higher up in frequency, and you don't have these huge spatial variations in that region. So that means that a concrete construction is more predictable when you measure it. And it's also by its very nature, because it's stiff and it's heavy, you will get lower levels down here in the low frequency region. So it's very important to know about this. You have to treat timber constructions with care, otherwise you might end up with very strange measurement results if you're not careful. And in today's video, I'm wearing a white shirt, orange knit tie, this patterned vest with lapels, which is kind of cool. Pair it with green pants and blue socks. And then I pick up some blue, light blue and dark blue. There's some white in here as well. I got light blue dots, dark blue socks, and green here, so the pants comes once again. So it's a lot of harmony in this outfit. And since I'm wearing a vest, I don't use a belt, because it looks nicer if you don't have a belt when you wear a vest. Sometimes I do wear a belt because my pants are a bit too large, some of them, so I need to kind of attach them harder. But if you can, get pants that you don't require the use of a belt, because they will look better when you wear a vest. And I think this white shirt gives a really nice contrast, especially with this tie. It really shines through, and orange is a great color. Have a nice weekend.